Okay. Okay, thank you. Okay, so first I would like to thank the organizers to propose to me to present our work in this conference. I will speak about two superconducting transition metal dichalcogenides, actually. One of them is palladium deuteride, which is a candidate for a topological superconductivity. And another one is NBS2, which is at the vicinity of the charge density wave and stability. So this work, palladium deuteride, is a collaboration with the Anna de Vissers group from Amsterdam. And the NBS2 is a little bit more my historical topic. And so it involves a lot of different collaborations. But what I will present, it's a lot of different work which has been done by my previous PhD student, Maxime Leroux. So the outline of my talk, first I will present a little bit the transition metal dichalcogenides, and I will speak about the two systems, so first palladium deuteride and NBS2. So the transition metal dichalcogenides are systems where you have two chalcogens, so sulfur, selenium, or telluride, and with one transition metal. Probably the most famous transition metal dichalcogenides are in blue here, but actually there is a very wide variety of systems. And the ground states are very, very different, and so you have very numerous possibility to observe some different kind of ground states, and a lot of them are superconducting. And so it's interesting to study how these different ground states can influence the superconductivity. One point which is very interesting also in these systems is the fact that it's quite easy to do some single layers with the transition metal dichalcogenides. And when you are doing this, few of them stay superconducting with a very huge hypercritical field, which is above 10, so far above the Pauli limit. So it's also a very interesting topic in this field. Actually, the variety of the transition metal dichalcogenides is also due to the fact that you have a numerous different kind of polytypes. So the transition metal form a triangular lattice and are surrounded by 6 chalcogen in the octahedral coordinations or trigonal prismatic coordination. Each layer, you can stack each together by different way and form different kind of polytypes. And the polytypes are with one number, which is the number of layers that you need in view to define the unit cell, and a letter which will define how each layers are each together. So the bond structure of these systems are quite often dominated by the D bonds from the transition metal. However, recently it was shown that the P bonds of the chalcogen, due to the crystal electric field and the spin orbit, are very important, because when you are going from the gamma point of the Brillouin zone along the C star direction to the A point, it's possible to have an inversion of the bond with a crossing of the bond without any hybridization. And so this, it will give some, the presence of Dirac cones in these systems. So one interesting systems in the topic of the topological materials in the transition metal dichalcogenides is palladium deuteride. Oops. So why? First, because the bond structure close to the Fermi level is really dominated by the P bonds from the telluride, and the D bonds are quite far away from the Fermi level. And it was predicted to have some tilted Dirac cones in the Fermi, in the bond structure, and it has been observed experimentally. So first by Joas van Alphen, since these Dirac cones intercept slightly the Fermi level, and so there is a small hole pocket which have been proved experimentally that it's indeed related to these Dirac cones. The second techniques which have observed these Dirac cones is the angular resolve photoemission spectroscopy, where you can see here along the gamma A line a crossing of the two bands. The second point is the fact that it was predicted that you have some surface state due to the presence of these Dirac cones, topological surface states in these systems, and it has been indeed observed experimentally here. So the point which is interesting with palladium deuteride, it's also that it's known that it's a superconductor. So the is to see if indeed there is some topological superconductivity. So basically, which will be related to an unconventional superconductivity in the bulk and also the presence of surface states. So little is known on the superconductivity properties of these systems. So it's the critical temperature is around 1.6 Kelvin. It's a type 1 superconductor. Actually, there is a quite isotropic critical field measured by resistivity, but also the normal state properties are quite isotropic. The point which is interesting, here you have the critical field versus temperature measured by resistivity. And so you see that you have a very small critical field around 0.3 Tesla. And a huge kink which is at very low magnetic field. In fact, if you are doing some magnetization or specific heat measurement on these systems, what you can observe is that the bulk critical field is at least 10 times less than this resistivity measurements, since it's around few millitesla, or tens millitesla. And the two lines are crossing exactly at the kink which have been observed experimentally. So the point is that it seems that there is some surface superconductivity which is unusual in this system. So the probe that we are using is the magnetic penetration depth. The magnetic penetration depth is the ability for a superconductor to expel an external magnetic field on a length lambda. And this length will be directly related at the zero temperature to the normal state properties through the average of the Fermi velocity along the surface, the Fermi surface, sorry. The second information that you can have is some information on the superconducting gap, since the temperature dependence of the magnetic penetration depth will be related to the excitation and how you destroy the perfect density. In fact, it can be calculated according to what is the gap structure on each part of the Fermi surface. But what is important to remember is the fact that when you have a superconducting gap which is open on all the parts of the Fermi surface, you will have a temperature dependence which will be exponential, and the curvature will be associated to the value of the superconducting gap. We are measuring this magnetic penetration depth. What you are using, it's a LC circuit which is driven by a tunnel diode. The superconducting sample is at the center of the inductance, and the variation of the magnetic penetration depth or the skin depth in the normal state will induce a variation of the resonant frequency of these systems. And the point which is interesting is the fact that you can work with a very, very low magnetic field, AC magnetic field, well below in the lower critical field. So experimentally, what we have observed, we have measured different samples of palladium ditelluride with different thickness. We have observed some few steps on the variation where the origin is not really clear, but is believed to be extrinsic. And the point, and only on few samples, and the point which is important is the fact that at low temperature, the variation of the magnetic penetration depth versus the temperature doesn't follow a power law, but more an exponential temperature dependence. And if you extract the value of the superconducting gap, what we found is something which is very close to the weak coupling BCS value. The second three parameters in this fit are the magnetic penetration depth, which is approximately half micrometer. If we try to do a rough estimation of the London penetration depth in these systems, what we found is something which is far away from the value which have been observed experimentally. And even if we take account the no-local correction due to the type 1 and also the mean free path, it's very difficult to reconcile this value with the value experimentally observed. So there is a discrepancy between the experimental value and the estimation. So is it due to the fact that we have a basic estimation for the London penetration depth, or is it something which is more intrinsic due to the fact that we have some unpaired electrons, maybe sensitive to the defects? So the conclusion on these systems is the fact that the superconductivity seemed to be very classical, with a superconducting gap which is fully open on all the parts of the Fermi surface. But we need to understand why there is a so large magnetic penetration depth measured. So the second point, the second topic of my talk will be to speak about the charge density wave and superconductivity in the transition metal dichalcogenides, and in particular in the case of NBS2. So the transition metal dichalcogenides, and especially the niobium and tantalum-based systems, are very interesting in view to understand the competition between the charge density wave state and the superconductivity. So indeed, more or less all of them show a charge density wave and a superconductivity. And the superconductivity can be changed quite a lot under pressure in few systems and not at all in others. So it's a very rich topic. One point, so a charge density wave is the fact that you have a modulation of the density of electrons near the Fermi level, and so there is a decrease of the electronic energy, but you have an increase of the elastic energy due to the fact that you have a distortion on the lattice. And what is important is that quite often what is observed, it is the lattice distortion and not directly the charge density wave. The lattice distortion associated to the charge density wave in the transition metal dichalcogenides and tantalum-based systems depend on the polytype. So in the case of the 1T polytype, what is observed is kind of a David star-shaped distortion, and you have a small distortion of the different transition metal lattice, which form these clusters of David star-shaped. In the case of the 2H transition metal dichalcogenides, the Q vector is quite different, and it's just along the A star axis. So what is important is when we have an octahedral coordinations in this family, we have a Q vector which is like that. When we have a trigonal prismatic, we have a Q vector which is like that. There is one exception on the competition between charge density wave and superconductivity. These systems, it's NBS2. So indeed, when you study the two isoelectronic systems, so NBSE2 and NBS2, here you have some STM measurements. What you can see, observe the moire effect due to the presence of the charge density wave in NBSE2, but in NBS2 it's not present. Actually, we have understood why we have no charge density wave on the system NBS2. And for this, what you need is to measure the phonon dispersion of these systems. When you are along the gamma K line, you have no temperature dependence of the phonon dispersion, which has been measured at 300 Kelvin and 2 Kelvin. And it's follow very well the ab initio calculation in an harmonic approximation. However, when you are along the gamma M line, so A star direction, what you observe is a huge softening of the phonon and a huge temperature dependence of this phonon, exactly at the Q vector where the charge density wave should appear. These results are not in agreement with the ab initio calculations done in the harmonic approximation. And in fact, this is due to the fact that the anharmonicity of the potential of the lattice potential is very important in these systems. And the temperature dependence of the phonon softening is due to the fact that we have an anharmonicity on the lattice, and so it will depend on the amplitude of the vibration. The point which is interesting, it's even at the lowest temperature, you have you prevent actually the formation of the and this is due to the fact that the zero motion vibration are quite strong enough in view to prevent the formation of this charge. So it's a little bit like the quantum para-electric, but here in the case of a charge wave system. In fact, it was calculated later with the anharmonic approximation in these systems, and indeed they show that you lift the instability, the lattice instability, due to the anharmonicity. The second point that they have done in their calculation, it was the gap, the variation of the superconducting gap on the different part of the Fermi surface. And what they show is that you have an anisotropy of the value of the superconducting gap with roughly a factor of 2 between the maximum and the minimum of the superconducting gap on the Fermi surface. So this, it's just due, I'm coming back on this point, it's just due to the fact that you have a small electron-phonon coupling constant in one direction, but a high electron-phonon coupling constant in the other one. And this variation of the gap structure was previously reported by our work. So first by magnetic penetration depth, where indeed you observe an exponential temperature dependence at very low temperature, but which is not compatible with the weak coupling theory, but by a small superconducting gap. If you plot the superfluid density versus the temperature on all the temperature range, actually you can fit this temperature dependence with an anisotropic superconducting gap with a ratio of approximately 2. So it seems that everything is quite well understood in these systems. Actually, it's not completely true, and there's one point which is quite important. Well, maybe not so important, but which should be noticed. So if you are doing some diffuse X-ray scattering on these systems, so here you have the basal plane, a cut of the basal planes, you have the Bragg peaks which are completely saturated, and you can observe between the different Bragg peaks some extra scattering, which is due to the fact that you have the phonon softening, which contribute to the diffuse scattering. But actually what you can observe also is some tiny extra spots which correspond to basically an intensity which is 10⁻⁵ less important than the Bragg peaks. These Bragg spots are elastic, so we have checked, and disappear when you increase the temperature. And it's possible to inject all these tiny spots with a Q vector, with one single Q vector, which corresponds to a charge density wave which is observed in the 1T systems. So we believe that it is something which is extrinsic in the sample, but the problem is to understand how is it possible to have this kind of coordination in a 2H structure. So the basic idea is to say that we have some niobium which is in octahedral coordination in few parts of the samples. So we don't know exactly how, if it's due to the fact that we have some staking faults on the layer of the chalcogen, or is it due to strains which will favorize a 1T structure, or maybe it's due to the fact that we have some interstitial niobium which is in the van der Waals gap and which will be in this octahedral structure. So to conclude, NBS2 is a system which is at the vicinity of a charge density wave instability, and this is due to the fact that you have a very anharmonic lattice potential. There is a small superconducting gap, and due to the fact a small superconducting gap and a large superconducting gap due to the fact that we have an anisotropy of the electron-phonon coupling constant. But everything is very robust on these electronic properties, but we have observed also some traces of charge density wave, which is characteristic of the 1T polytypes in these systems. So thank you for your attention.